Have you ever heard or seen news headlines proclaiming the discovery of so-called super-Earths? This term applies to a planet with the allure of being Earth-like, only larger, and with more room for life forms to roam. A planet with more resources to support an ever-growing demand. Is there reason for such hope and optimism that these super-Earths are just larger versions of our own home? Or is this merely an unfortunate name that gives us a false sense of hope for finding intelligent beings? Next, we'll discuss this possibility and some unexpected findings from the study of exoplanets. Stay tuned. Our solar system has two types of planets, the terrestrial, or Earth-like, and Jovian, or Jupiter-like. Terrestrial planets are small, have rocky surfaces, thin atmospheres, and are relatively close to the Sun. Jovian planets, in contrast, are relatively large, massive, and gaseous with no solid surfaces. They're also distant from the Sun when compared to the terrestrial planets. In our solar system, the asteroid belt divides these two types of planets. To put the two types into perspective, the Earth is much smaller than even the smallest of the gas giants. So that describes our solar system. How does it compare to the findings of over 4,000 confirmed exoplanets? The data shown here shows an overwhelming number of super-Earths, that is, planets with sizes ranging from about 2 to 10 Earth radii. Note that current techniques favor the discovery of larger planets close to the parent star. Therefore, there may be some bias in these results. So keep that in mind as we go forward in this conversation. Super-Earths, it seems then, would conjure images of a larger Earth-like planet with more available real estate, one with more resources, and a thicker oxygen-nitrogen atmosphere. But not so fast. We know that a planet's atmospheric composition depends upon four factors: the planet's mass, the planet's radius, the nearest star's temperature, and the distance from that star. This topic is covered in a separate video. Current planetary formation theories explain that the solar system formed from a collapsing cloud of debris with similar composition throughout. Therefore, all planets started with an initial hydrogen-helium dominant atmosphere. Since different locations in the cloud had different temperatures, the planets large and cold enough held on to the lighter elements. Those smaller, hotter planets held on only to the heavier elements. Small planets in close proximity to the Sun, like Mercury, are too hot to retain any atmosphere. Pluto, a smaller body than Mercury, does have a thin atmosphere. However, Pluto is very distant and very cold. At the coldest temperatures, even small bodies can retain a thin atmosphere. Note that Pluto's atmosphere may not be a permanent atmosphere. It may be replenished by volcanism or other geologic activity. Future studies will resolve the origin of Pluto's atmosphere. Larger distant planets like Neptune and the other gas giants are far enough from the Sun that all of the light elements can be retained. A notable exception is Saturn's moon Titan. It is small by Earth standards, but has a thicker atmosphere than even Earth. This seems to contradict the theory. However, remember that Titan is also very cold and retains only the heavier elements in its atmosphere. Little to no hydrogen and helium is present. Note that atmospheric composition can also change due to reactions with sunlight, geologic activity, or biological processes. With over 4,400 exoplanets currently known, four basic types emerge: terrestrial rocky worlds that are Earth-like, gaseous worlds with large volatile envelopes like Neptune, the very massive ones that are currently undergoing gravitational compression like Jupiter, and finally, full-fledged stars that grew rapidly by the same process planets formed from, eventually reaching temperatures hot enough to start fusion in its core. Super-Earths would fit somewhere between terrestrial and gaseous. What then is the determining factor, and what is the value of that factor that leads to the Earth-like path or the Neptune path? Studies indicate that planets have a distinctive cutoff around 2 Earth masses. Planets larger than 2 Earth masses show a sharp increase in radius, giving rise to Neptune-like planets. The data leads to the following conclusion from one study's author. Once you get to be about 2 times as massive as Earth, or about 20 to 30% larger in radius than our planet, you're no longer rocky with a thin atmosphere, but are overwhelmingly likely to be Neptune-like, with a full-fledged large envelope of hydrogen, helium, and other light gases. Venus, with an atmospheric pressure of 90 times that of Earth, might seem tame by comparison. Looking at the population of planets from the known exoplanets also reveals a large gap of Earth-sized worlds at a similar 1 AU distance from its central star. Why is this significant? Most of the exoplanets are around Sun-like stars. The habitable zone, as it's called, is around 1 AU, but does depend upon the central star. Planets not near this habitable zone have significantly lower chance of having liquid water, a condition for life as we currently know it. If a planet is in the habitable zone, it doesn't guarantee that life exists either, especially if the planet is too large. This leads to the conclusion that Earth may be nearly as big a planet as a habitable planet can be. A larger planet leads to a thinner crust for life to inhabit, greater attraction of asteroids and comets with potential for wiping out any life, a thicker atmosphere which affects the temperature, oxygen content, and weather on the planet, and it presents a much greater challenge to physically leaving their planet. Of course, other limitations will apply, and we go into these in the video on the Drake equation. Finally, our home planet may in fact be more unique than we imagine.
We had a slight weapons malfunction, but everything's perfectly all right now. We're fine. We're all fine here now. Thank you. How are you?
We're sending a squad up.
A negative. We had a reactor leak here now. Give us a minute to lock it down. Large leak, very dangerous.
There's no reactor on that floor.
Yes, well, I talked to Dave Johnson in Stormtrooper Engineering, and he said there is a reactor here.
Dave Johnson? Hang on one second. Okay, I have Dave Johnson on the line. Dave, did you tell someone there's a reactor in prisoner control room?
No, there's no reactor there.
Well, I don't know what to tell you, but I'm staring straight at a reactor. Maybe Vader had it installed yesterday.
Hang on a second.
What do you want?
Lord Vader, did you install a reactor in the prisoner control room?
Not that I know of. Hang on one second. Sheila, can you get me the plans to the Death Star? Okie dokie. Got the plans here. Let me have a look. Boop-a-dee, bop-bop, reactor. Boop, boop, boop. No reactor that I can see, but might as well put one in. There's always room for another reactor.
We'll send a team up to build the new reactor.
No, not necessary. We've got it under control. We're in conversation anyway. Okay, let's build this reactor.
I love you.
I know. That I did not know. You know, I've never met another Wookiee, Chewie, so it'll be great to finally meet your family. You mean to tell me you've been naked all these years?